Hello, my name is Paola Barrios,
Hi, my name is Joanne.
and we are both MSAI students in the 2025 Computer Vision course. And today we're going to be talking to you about our surgical instrument tool tracker. We're very excited to show you guys. So we decided to do this project because we felt like it was a real problem that we could solve with our computer vision skills. Basically, during surgery, it's important that all the tools that are being used are accounted for. So basically saying that the count before the operation must equal the count after the operation. This is important for a couple of reasons, but you don't want to lose your instruments, but mainly you don't want to leave an instrument behind in the person's body. And so the nurses in the operating room currently take a lot of time out of the operation and out of their job to count the instruments and to make sure that at all moments during the operation they have the correct instrument count and that nothing's being left behind. This can be distracting for them if they have to focus on a different task that's not really related to the operation. It's time consuming. Every time they count, they count all of the instruments. It's also quite inefficient because it's a manual count that requires two people double checking each other, counting multiple times for accuracy. And again, it's important because we don't want to lose these instruments. And so we figured that this would be the perfect place to apply our computer vision and hopefully build something that can help either track instrument count or, just count our instruments for our nurses so that the staff can focus on what's important during the operation, which is the patient. And so our main aim here was to find an easy way to keep track of surgical instruments during the operation. And we came up with two different approaches, two different ways that could be done, and we explored our computer vision skills. The first one was photo detection. The basic idea of this is that you could take a picture before the operation starts with all your instruments and count that, and then take a picture after the operation's finished and then count that as well. And hopefully your counts match. And if they don't, then you know that there's an instrument missing somewhere. Along with this, we would like to know which instrument is missing. So we went a little bit further from this and said, let's try to classify these instruments using some of our computer vision skills. We also try to do this using video tracking, live video tracking, where as the instruments move in and out of the frame, you kind of account for all the instruments and it automatically just counts with movement. And then that way you kind of know where all the instruments are at all times. And so, as you may imagine, we had some challenges with our environment that um, are likely also challenges that would have in the real world in an operating room. The first one being that these are all different instruments, um, and there's very subtle differences between them. For example, in this picture here, representative picture on the screen, you can see that the needle drivers at the top have a blunt end and they have rings to them. But also scissors, which are found right here bottom left, also have rings to them, except they have a sharp end. And this came into play mainly when trying to classify our instruments and also trying to find ways to pick up all our instruments regardless of what they look like. We also had some challenges with lighting variations. Of course, in the operating room as well as in our pictures, you can see the bright light shining from the top. That gives you some reflections kind of here and here, and also some shadowing, which made it a little bit difficult for us to pick up our instruments, but finally prevailed. And the last one is that the surgical room and the surgical table where the instruments lay is a dynamics environment where there's a lot of movement. There are hands going in and out of the frame, causing occlusion, and things are happening quite quickly with multiple instruments sometimes moving at the same time. In addition to that, no, the instruments are not always lined up nicely like they were in the last picture. Sometimes the instruments, as the operation goes on, they get a little messy, and so they sit on top of each other, just as shown in this picture here, which was another challenge that we faced. And one more thing is that not all instruments that are accounted for are metallic or have, this gray hue to it. Some of them are not metal at all, and these are also supposed to be counted. And so we also had to adjust for that. So in the bottom right here, it's a piece of suture that also needs to be counted in a normal surgical count. So our first approach was instrument ID and counts with photographs. And here we used 5 steps basically. The first one being channel separation from our color scale versus our lighting scale. This was trying to separate all the lighting and different shadows that we may encounter from the actual colors. Then we applied color-based segmentation, and we really took advantage of the fact that the blue towel is so different from the instruments. Um, and this is something that actually happens in operating rooms. There's a blue towel at all times in the background, and so we figured that we could replicate that. This was okay because this is what's happening in the real world, but we played that to our advantage as well. So we had multiple masks where we first masked the blue towel, then masked the instruments, inverted the blue towel so we could pick up the instruments. Um, and then had a components mask as well, which I'll show you in the next slide, and then ultimately our count. We use connected component analyses to connect the contour of our instruments to make sure that when the contour connects, that's one count or that's one instrument. And then for our classification, we use a lot of base-shaped filtering. We also play to the advantage the fact that these instruments are a little different. Some of them have rings for fingers, some of them are blunt, some of them are sharp. And so we had to do a little bit of playing around with that as well to pick up what the different instruments were. And of course, when we classified and when we separated our instruments, we were very conservative in the morphological processing. We used small kernels to remove noise because we didn't want all of them to merge into one. And it's really important for us to keep the instruments separate. And so here are some of our initial results. These are results that worked. Um, so here on the panel on the left, you can see the original image. There's 1, 2, 3, 4, 5, 6, 7, 8 instruments in the image. This is then we applied our instrument mask where we basically subtracted the blue towel from it. And you can see it's doing that really, really nicely, picking up our instruments. These are a component mask, same thing, picking up our instruments quite nicely. And then at the end, using our or looking at our number of detector instruments once we've applied all the techniques that we discussed in the previous slide. And you can see here that it's boxing instruments appropriately 1, 2, 3, 4, 5, 6, 7, 8, and it in fact detected 8 instruments, which we're very proud of. And then on the right, you can see how our classification went, which was good, but still needs a little bit of work. Again, the total count being 8, 5 hemostats, which really there's only 4 hemostats here, but it's counting the scissors as hemostat as well. And, you know, easy mistake to make because they look exactly the same except for the tip. So it's a challenge that we're still working through. And we did apply, morphological tip detection, but I think it's just picking up something else as scissors. So it's picking up this forceps as scissors also because it has a sharp tip. So we're working on that still, but overall pretty good results. Um, this is how our blue towel kind of helped us. Um, we decided that our field of interest was in fact the blue towel, and that anything that was outside the blue towel was not going to be in the count. So that's just a requirement for a project, and also a requirement in the operating room. If the instrument's not on the field, it doesn't count. Everything has to be there. And so you can see how it nicely kind of excluded that one, and the instrument count remained 8 because it wasn't on the blue towel. And again, we talked about how not instruments are metal, and we were very happy when we successfully also detected the suture, which was not metal, in this picture here with 5 instruments, and also detecting the suture material. So that was great. And then something that didn't work, which we're also still working on, is the fact that these instruments are on top of each other. And so you can see sometimes it just kind of it just puts 1 or 2 instruments as one, and it thinks that that's one instrument. And then the other ones get ignored when it's focusing on that. But um, something to work on.
So I'll be talking about the video part of it that we worked on. The first thing that we did, very similar to the images, was finding that region of interest detection, which we'll refer to as the ROI. Essentially, we wanted to identify that blue surgical cloth and wanted to keep that as something that, count all the instruments within that space. And so we used the HSV color space. What we did was convert the frame to the HSV color space, and we created a blue mask using very specific HSV ranges. And we applied some morphological operations to kind of clean up that mask. We found the largest contour, which was assumed to be the surgical cloth. And we applied some erosion to shrink the ROI inwards, avoiding any edge artifacts. We made sure that this was also dynamic ROI. The reason being that as you're taking the video, it tends to move. And so every 5 frames, we would actually make sure that that ROI got updated, which helped to adapt to movement in that surgical cloth. For the instrument detection itself, and we'll show a graph. We actually did some saturation channels, and we plotted it, and you will see kind of two bimodal distributions for what they picked up. And this worked well in our favor as well. What we were able to do is extract the saturation channel, and we found that instruments typically have lower saturation than the blue cloth. We were able to add some thresholding for some automatic threshold selection, and we additionally put in a detection for darker instruments. As you can see in some cases, like you'll have these instruments either on its side, it'll appear darker than the rest of them. And at the end of the day, we were able to kind of apply some morphological operations, clean up that binary mask, and pick up the instruments. Now, again, like we talked about in the images, you have skin and hands coming in and out. And so we wanted to do some skin segmentation and removal as well. And that kind of helped when we learned a little bit about that in our computer vision class about the YCRCP color space detection and HSV color space detection, which is what we used. We used two separate ones, and then the two masks were combined. And then we did some morphological closing and opening as well, cleaning it up a little bit, adaptive dilation based on the amount of skin that was detected. And then the dilated skid mass was subtracted from the instrument detection. We ultimately then moved on to instrument counting itself, and we put some configurable values in there. Number one was like the area. We found that having that area that was between 700 to 15,000 pixels actually helped, because if you were to give it too low of an area count, it would then pick up random artifact as maybe instruments. An edge margin, we made sure that it was at least more than 10 pixels from the edge images. An aspect ratio more than 1.5 so that it favored elongated objects. The reason being that most of the objects in the OR, they're elongated. There's nothing really truly circular. And so even for circularity, we made sure to kind of reject those circular objects when we put it in. Solidity, we made sure that it was there as well. It was a ratio of the contour area to the convex hull area. And we did all of those things and did a centroid validation as well. So this was to calculate the centroid of each contour and verify that it felt within that strict ROI mask. The last thing we did was something called temporal stabilization, which in this case is very important. The reason is because it prevents the displayed count from jumping around erratically. So when we count instruments frame by frame in a video, the raw count might flicker between values, like it'll go 4, 5, 4, 5, because lighting changes, slight movements of hands, even detection errors at object boundaries. Even though no instruments are being added or removed, the count just bounces back up and down. To solve this, what we did was we made sure that the system remembered the count from the last 30 frames, so about 1 second of the video in a rolling buffer. So instead of showing the current frames count directly, it looks at the most recent 15 frames and then finds the mode. That's the number that appears more frequently. For example, if the last 15 frames showed counts that were like 4, 4, 5, 4, and bounced around a lot, the mode might be 4 because it was appearing 10 times compared to the others. So it only displays 4 as a stable count. Now, this made sure that it was smooth, steady display, only changes when there's a genuine sustained change in the instrument count, eliminating that annoying flickering that would otherwise confuse people in the OR. So basically, it's like if you apply like a majority vote to recent measurements, so occasional detection errors get outvoted by the consistent correct method or count, resulting in a reliable display that people can actually trust. So kind of this was a summary of what we did. Let's take a look at the videos and the images themselves. So when we look at the videos, you can kind of see that green boundary, which shows the region of interest. That's the blue cloth that dynamically would change as the video was playing. The yellow contours are around detected instruments. The red dots are the centroids. We have some numbered labels for all the instruments as well, and the count display both the raw and stabilized on there. And we had optional indicators as well for dynamic ROI updates. This approach was good because I'm going to talk a little bit about that saturation channel as well a little bit later on. So if we go forward to the next slide. This is the one. So this is kind of talking about why our method really worked well. And when we look at the saturation distribution, we can kind of see that x-axis shows the saturation values from 0 to 255. And the y-axis is the pixel count. The red dashed line is that threshold. And we can see there's two distinct population, which is perfect for us because we're able to kind of put that threshold and accurately detect which one was which. The one that you see that's quite high, the peak around 150 to 200, that's the blue surgical cloth, high saturation. And we noted that all the small distribution below 100 was the surgical instruments. And again, the thresholding that was applied just worked beautifully because it was able to distinguish between the two. Now, the histogram showing these two peaks is kind of what we wanted to demonstrate as well in this graph. Um, and the red line is the OTSU's automatic thresholding, which places a boundary, which kind of falls perfectly within that valley between the two peaks, so that we know that the basically method worked correctly in identifying that optimal separation point. So this wide gap between the two populations, roughly 550 to 100 saturation values that we can see, means that the system is robust to lighting variations, different instrument types, minor color variations in the surgical cloth. So it just worked out really well in our favor. And even the OR, like Paula mentioned as well, everything gets placed on a blue cloth. And so everything that falls within that visual viewpoint is what should be counted. So let's watch a couple of videos of our code in action. As you can clearly see, it kind of keeps account segments out the hand or coming in and out of the frames. And the green outline kind of stays around that region of interest and changes every few frames that you can see because the video itself is moving, but it keeps updating itself. What we really want to focus on is that count at the beginning and the end, which stays pretty accurate, as you can see. Occasionally, occasionally, as we do see, sometimes it does kind of miss or count the edges as an object, uh, but overall, kind of does a good job. This is another one as well with fewer instruments and easier to detect ones. In the first video, as you could see, the instrument that really was missed some of the time was the one that was on its side. And so we were trying to find ways to improve that because it appeared darker than the rest of it, at least visually, and we think that's probably why it didn't get picked up as much. Okay, and then some limitations that we'd like to talk about was basically overlapping instruments. We'll play a video for you showing kind of what the code does when it's overlapping, but from the image itself, what you can see is it picks up those two overlapping instruments as a single one is number four, even though to us visually they're two separate scissors altogether. So to improve the detection of overlapping included instruments, we're thinking that maybe in the future we could maybe include a multi-camera setup, maybe 2 to 3 cameras positioned at different angles. So maybe we can see instruments that are hidden from one viewpoint, maybe visible for the others. And when they're overlapped or stacked on top of each other, maybe we can use like a stereo vision system. So like two cameras, providing some depth information. So it can allow the algorithm to distinguish between instruments at different heights, rather than merging it into a single detection. And again, for the specific problem of instruments being held in hands, we were thinking it'd be cool to maybe like have dual pipeline approach where we have one for the instruments on the blue drape and the other specifically for tracking instruments as they're picked up. So we would actually know what was picked up, which instrument was picked up, maintain their identity, and kind of make sure that it's tracked as they leave the surgical field, that blue sheet basically. Additionally, maybe some edge-based separation algorithms could actually help split our merged contours where instruments cross or touch, maybe detecting the intersection points and separating them into individual objects. We also thought maybe some machine learning could help in actually identifying which instrument was which. So, for example, like we talked about before, it didn't do a good job of like saying exactly which one it was, whether it was a hemostat, a scissors, a tweezers. And so maybe if we used a little bit more training, large annotated labeled data set, we could actually be able to train the system to pick it up, know what it's looking at, and then maybe apply that with some computer vision techniques to actually be able to pick these up and actually give a good count, but also be able to tell us what is missing from that visual field. Um, yeah, thank you.